problems involving the greedy pattern are actually very fun to solve. Well, that is when you have identified what will be your greed criteria. And the hardest part is proving the fact that your local maxima or your local optimum solution will eventually lead you to the global optimum solution. Once you have proved that, most of these solutions work in a linear time complexity. So how do you go about solving that? We are going to look at some of the problems that involve a greedy approach, and by the end of this video, you may start to get an idea when you can apply this pattern. What factors do you need to look out for, and how can you start to think what is your greed criteria and how can you take advantage of that? So let us dive away straight into the problems. Hello friends, welcome back to my channel. Let us do a quick recap on how the greedy pattern actually works. The idea is fairly simple. You are given a sample space. What you do is you choose the local optimum solution from your available sample space. After this, you take up this solution and add it to your final solution set. You will still be remaining with some other sample space, correct? For a greedy approach, you want to just keep doing this process iteratively. From this remaining sample space, again apply the same technique and choose your local optimum solution, and then add it back to your solution set. This way, you will keep on building up your solution set, and by the time your sample space is empty, you hope that whatever solution you achieved is the global optimum solution also. Now, all of these are words. How do you actually apply this algorithm? Let us look at the very basic problem, something that we all have been doing without even thinking about it. And this is the main crux of how greedy algorithms actually work. So let us say I have this set of integers. And now I ask you, okay, use these integers and construct me the largest integer possible. Without even thinking, what will you do? You will pick up the maximum integer that you can find. Over here, it is a 9. So what you're going to do is you will add 9 to your solution set and remove, let's say, one of the 9s from here. You are now left with another sample space, a smaller sample space. Again, you will apply the same technique. Find out the local optimal solution. Out of these integers, what is the largest? It is 9 again. So you pick up this 9 and then this gets removed. What is happening over here? After each iteration, your sample space is reducing and you are using the same technique to pick up the optimal solution. Once again, from this sample space, you will pick up the maximum integer that you can find. So this time you will find a 7 and you remove this from your original sample space. Similarly, then you will get a 6, then you get a 4, then you get a 1, and then you get a 0. You kept on applying the same technique, trying to get the maximum integers from what is available to you. You kept on repeating this and you got the global optimal solution. You cannot have an integer larger than this that can be constructed from this set of integers. So over here, our greedy approach worked perfectly. But the caveat over here is that you need to be a little careful when it comes to greedy algorithms, because sometimes the greedy approach may not be the optimal one, or it may not even lead you to a correct solution. For example, think like this. Let us say there is a mountain, correct? And you are standing over here at the bottom. What does a greedy approach say? If you have to climb to the top, what is the shortest path? Just go straight ahead, right? This is the shortest path. But it is a mountain. So an optimal way might not even look like this. You might have to traverse a lot of different paths and you might have to take different turns to finally reach the peak. And that might be the optimal solution. Sure, there might be a lot different other ways to go around the mountain, but there will be one global optimum way which you can be arriving in the shortest possible way, correct? So this is a typical scenario in which a greedy approach might not be successful. So you have to be a little careful when applying the greedy algorithmic approach. So this gives you your first pointer. When can you apply the greedy algorithmic approach? Basically, when you have determined that the local optimum solution will lead you to the global optimum solution, greedy approach is your friend. It will be fast, it will be linear, and it will work efficiently. But if you see that there are some interdependent steps, if there are subsequent steps which affect how you would have approached over there, then you might have to look into alternate solutions also. And that is where other programming techniques like dynamic programming come in. you are building upon different solutions. So this is the first thing that you need to watch out for. And what we just discussed was a standard example of how a greedy approach would look like. You might have seen its application in a lot of different places. For example, when you are giving change to a person, how do you start? If you have to give them the minimum number of currency notes, what do? You start with the biggest note that is available to you. And then you go on to the smaller notes. So your greed criteria is, I will pick up the biggest note that I can pick up right now. If you cannot do that, choose the next biggest note. And that is how you can guarantee that, okay, I will give them the minimum number of currency notes. So all of these are very standard examples that you see in everyday life. How about some coding problems? For example, let us take a look at this particular problem, assign cookies. The problem is very, very simple. There are some children available and they are hungry. So children 1 has a hunger criteria of 1, child 2 has 2, and child 3 has 3. And you have cookies available. Now each cookie is a different size. It simply means that if the cookie size is 1, then you can satisfy one of the children whose appetite is also 1. Similarly, if this child has an appetite of 2, they will need 2 cookies. And a child of appetite 3, they won't be able to be satisfied with the cookies that you have available. So given all of this scenario, you have to tell me how many maximum children you can satisfy from their hunger. Over here, if I don't apply any algorithm, I pick up, let's say, this child in random. This child has a hunger of 3. But I have cookies available for a maximum appetite of 2. So can I satisfy this child? No. So I am out of all my cookies and none of the childs are satisfied. So how do you go about it? You will apply a greedy approach. What you're going to do is you are going to sort the children in the order of their hunger. So the first child will have the least hunger and the last child will have the maximum hunger. And similarly, you are going to sort the cookies available to you as well. If you have the smallest cookie, that will be in the beginning and the largest cookie will be at the very end. You will start with the first child. Now, whatever the hunger is, start giving them cookies until their hunger is completely satisfied. This particular child gets satisfied with 1 cookie, so this is done. The next child has a hunger of 2, but you have only 1 cookie available. Can this child be satisfied? No. So the maximum number of children whose hunger can be satisfied is just 1. So 1 will be your answer in this particular test case. Now let us try to look at a bigger example and that will make things clear. Over here I have 6 children available and as you can notice, they all have a different appetite. Similarly, this time I have 5 cookies and all the cookies are of different sizes. First thing is very obvious. I have 6 children and I have just 5 cookies. In no way I can satisfy all of the 6 children. So the answer will be less than or equal to 5. That is guaranteed. But can you satisfy all these 5 children? Let us check it out. How do you go about it? First of all, what I'm going to do is I will sort all of my children's hunger. They are now sorted in an ascending order. Similarly, I will sort all of my cookies also. Now what I will do is I will start assigning these cookies one by one to each of the children. For the first child, I take up the first cookie and I give it to him. His appetite is satisfied. So okay, first child is happy. What about the next child? He can get a cookie of 2. So he is also happy. What about the next child? He can get a cookie of 2. So he is also happy. Meanwhile, I'm done with 3 cookies, right? Look at this next child. He has an appetite of 3. And I have a cookie available that is of the size 4. So what do? Do you give this cookie to this child or do you skip this child and maybe wait for another child? My greed criteria says that if I have a cookie available, just give it to the child and then we'll worry about the future. So what I'm going to do is I give this cookie to this child and now this child is happy. Notice that I am done with this cookie. I cannot take the remaining cookie and give it to the another child. For the next child, he has a hunger of 5 and I have a cookie size available of 5. So I can give it to the child. This cookie is gone and this child is happy. So with the greedy approach, I was able to satisfy 5 children and I gave them the cookies that they needed. So this is how you can come to the solution. But the important thing over here is How can you guarantee that your chosen greed criteria will lead you to the global optimum solution? How can you be sure that there is no other way to make more children happy? The idea over here is you need to think counterintuitively. What if you weren't sorting cookies? Or what if you weren't giving the first cookie to the smallest child available? Or the smallest cookie to the child with the smallest hunger? Think counterintuitively. If you give a bigger cookie to a child who has a smaller hunger, then potentially you are avoiding the other children to be happy. So this is kind of paradoxical. That is why I can guarantee that if I go ahead with this greed criteria, I will be able to achieve a global maximum solution or a global optimum solution. Don't worry if this is not clear to you in the first time. More the number of problems you solve, the better you will get, and you will get an even better intuition. Let us look at another problem which obviously involves the greedy pattern. Over here, I am given a particular string and I have to find out the partition labels. The idea over here is that you have to return me the maximum number of partitions possible such that no two partitions have the same character. So what you have to do over here is you have to separate this string in a certain way such that no two partitions have the same character. If you notice, both of these partitions, they have independent characters. If a character occurs in this, you won't find it in here, correct? Had the question been about the minimum number of partitions, what you will do? You will simply take up just one partition and it can have all of the characters. Now, there is no other partition which has a different string. But the problem is not asking you for the minimum number of partitions. I want to separate it in such a way that I can have the maximum number of partitions possible. So how do you go about it? Where do you start? Try to think like this. If I pick up my first character, then no matter what happens, my first partition will have the last occurrence of this character, right? And I'm gonna use this as my greed criteria. So what I do over here is I iterate over my entire string and capture the last occurrence of each of the character that is available in my string. If you think about the first character, that is A, what is the last occurrence? This is the last occurrence and it is at the position 8. So what I do is I store this in some kind of a map. I know that the last occurrence of character A is 8. Now what about B? I keep on scanning my string and try to find out wherever is the last occurrence. The last occurrence is at the number 5. Now go ahead, check for character C. The last occurrence of character C is at the number 7. Similarly, you keep doing it for each of the character that is available. And notice, you can just do it in one iteration. You can start going from the back and then keep on updating the last occurrence of each of the character, right? So once you have built this entire map, how can you go about solving this problem? What I do is I start off with my first character that is available. I start off with the character A. I can check my map. I know that the last occurrence of A is 8. So no matter what happens, my first partition has to be up to the length of 8 at least, correct? This is my minimum length of the first partition. It can be even longer also. But to verify it, what you will do is you will look at each of the character in the partition that you have selected. For each character, check the last occurrence. If the last occurrence is greater than 8, then I am gonna extend this window. Otherwise, I don't need to do anything and I can stop right over here. I found my first partition. Now, how do you go about your second partition? I will start off with the first character, that is D. What is the last occurrence of D? It is 14. So it is for sure that my second partition will be at least up to the length of 14, correct? It could be longer and we have to verify it. So in this particular window, I will start looking. Check the last occurrence of E. The last occurrence of E is 15 and it means that I need to extend my window. My window size has now increased, but my logic will still remain the same. Now I will check for F. F is 11, so I'm good. E, then G. G is 13, so I'm still good. D is 14, so I'm good. E is 15, so I'm good. My window ended. So I got my second partition also. Similarly, what you're going to do is you will start off with your third partition and try to include the characters while looking from this map. I have left this last partition as an exercise for you. But what did we do? Just by applying the greed criteria that I want to include the last occurrence of the first character, I was able to construct this map, and then in just a single iteration, I got my solution. So in the end, I have 3 partitions and this will be my answer. From all these examples, what are we learning over here? We are understanding that greedy algorithms have some pros and cons of their own. First of all, they are intuitive and simple if you have understood the greed criteria. And they can be efficient and usually work in a linear time. But you must try to understand that your algorithm may not always be optimal if you haven't determined that your local optimal solution will lead to the global optimum solution as well. Also, you need to be a little careful with it. If you haven't looked up at all of the different options, just a local optimal solution might lead you to missing out some of the better solutions available. And all of this was just to get you warmed up. Now let us start looking at more problems where the greedy solution might not be obvious at the very first instance. For example, check out this particular problem, gas station. Over here, you are given, let us say, n number of positions. Each position is a gas station. And this is the available gas at each of the stations. You are given one more array. This array tells you the cost required to travel from one gas station to the other. So, for example, if you are at this particular gas station, you can only fill gas up to 1 unit. And to go to the next station, you will require gas of 3 units. So, basically, if you are starting from this particular point, you will only get a gas of 1 unit, but to go up till 2, you need 3 units of gas. So you cannot even travel over there. You will run out of gas in the middle. The idea over here is that all of these stations, they are connected in a circular loop. So you have to tell me, first of all, hey, is this trip even possible? And if yes, you have to tell me the starting station. If you think about it, you cannot start from this station. You will run out of gas immediately. Can you start from this station? No. Because you can fill up the gas of 2 units, but to go from here, you need a gas of 4 units. So once again, your gas will be emptied half the way and you cannot begin from here. What about the next station? Even for this, the gas is 3 and the cost is 5. So you cannot go ahead. What about the next one? Maybe yes, because you have 5 units of gas that you can fill up and it will only consume 1 unit of gas to go to the next station. So this might be a solution. And if you go iteratively, you will be able to determine if a trip is possible or not. But how can you apply the greedy approach? First of all, to determine that is a trip even possible or not, what do you think? The most naive solution is that, okay, to travel this particular distance, I should have at least this gas, correct? Think about it. If I have to travel a distance that requires 10 units of gas, I should have at least 10 units of gas to fill up, right? If the total gas available is less than 10, then this trip is not even possible. You can simply return a false. So the first step is to add up all of these numbers and check out the total gas required. This sum turns out to be 15. And you need to check, are 15 units of gas available? So you add up the total gas also, and this number also turns out to be 15. So one thing is for sure, this trip is possible. But where do you start? To determine it, all you need to do is just iterate over each of these gas stations one by one. You know that you cannot start from here. Can you start from here? No, because only 2 is available and it takes up 4 gas. Can you start from here? No, because 3 is available and it takes up 5 gas. Can you start from the next station? Yes. So if you can start from the next station, what you need to do is you need to check if you can reach the very end of the array. If you can reach the very end of the array, it means that you will be able to complete your trip. Because we have already determined that this trip is possible because that is the number of gas available. So no matter what is the distribution of gas in all of these stations, I will still be able to complete my trip if I can start from any of this particular index and reach the very end. So once again, the greedy criteria came to my rescue. The next problem I want to talk about is the jump game problem. You are given a certain array and I am standing over here at the first position. Each of these numbers, they represent the maximum number of jump I can take from this particular position. It means that if I'm standing here, I can just take a maximum of 1 jump. If I'm standing over here, I can take a maximum of 2 jump. I can either take a 1 jump or I can take a jump of 2. If I'm standing here, then I can take a maximum of 5 jumps. And it is up to me, where do I want to go? It is up to me how many jumps do I want to make. Now, you have to tell me if I can reach the last possible position or not. So, how do you go about it? How do you find out if it is even possible? To simplify this problem, we are going to look at an even simpler test case. This array is very small, and if you notice, there are no zeros in the array. So what does this tell you? It simply means that if I'm allowed to take any number of jumps, and none of the element is 0, from each of the place, I will be able to take a jump of at least 1, correct? And no matter whatever these numbers are, I will always be able to reach the end. So you can straight away dismiss one of the cases. If none of the numbers are 0, then you can always reach the very end. So one thing is completely sorted. Now what about this particular specific case? What do you do over here? What I can do is I can start to look from the very end. I have to reach over here, correct? Now try to start going back. If I was standing at this particular position, then can you reach at the very end? Yes, because after this, none of the numbers are 0. So will it be safe to narrow down the problem to this criteria? That if I am able to reach this particular number, then I will be able to reach at the end, correct? So I have already shortened out my problem, correct? Now let us try to apply the same logic. Can I reach from here if I'm starting at this particular number 0? No, because I cannot jump. So definitely this is not viable. Can you go to the last position if you're here? Once again, no. Can you go to the last position if you're at 1? No, because from here you can only take a maximum jump of 1. So keep going back. Can you reach from here? Once again, no, because from here you can only take a maximum jump of 2. Keep going back. Can you reach the end from here? Yes, because you can take a jump of 5. So 1 won't work, 2 won't work, 3 no, 4 no. How about 5? Yes. So if I can somehow reach this particular position, I will be able to reach my very end, and if I am here, I can reach the very end of the array also, right? So what I just did, I narrowed down my problem once again. If I can reach this particular position, then I can straight away reach the last position also. So what I'm doing, for every iteration, I am trying to narrow down my search space and I am applying the same greed criteria. If I can reach here, then I can reach here and then I can reach here also. So as I don't have any zeros available, I know that I can reach this particular number and then I can reach here and then I can reach here. So once again, I can say that yes, I am able to reach the last position. And once again, I use the greedy criteria. Over here, you just had to find out if a jump to the last position was possible or not. There is one more variation available of the problem where you have to tell me the minimum number of jumps required to reach the very end. And once again, greedy approach is your friend over there. What you basically do is your greed criteria will be what is the maximum jump or what is the maximum window available where you can land from your current sample space. So that's how I will start. For example, this is my current sample space. I can only advance one other position. So this will give me one more sample window. In this sample window, how far can I go? Once again, I can only jump one more position. So that's it. Now, what about this window? From this particular window, how far can I jump? I can jump a maximum of 2 spaces. So this is my new sample space. What are we doing over here? We are doing the jumps required. So up till now, I started from here. So one jump, then two jump, and this is the third jump. In my next jump, I will have to choose from this particular sample space. So if I can take 5 jumps, this is the maximum that I go. If I take 2 jumps, this is the maximum that I can get. What is this telling me? It is giving me the next possible window. So in the next possible window, I will have all of these numbers available. And now, once again, repeat the same process. For this window, now determine how far can you go. This will only land you here. These two numbers won't land you anywhere. This number will land you over here. So this is giving me my last jump that I will have to take. And that is how you will reach your end. So how many jumps did you take? You took a total of 1, 2, 3, 4, and then a 5. The minimum required jumps are 5. So once again, your greed criteria defines how will you approach the problem and how can you arrive at the most efficient solution. You might have to think, why is this local optimum solution the global optimum solution? Because when you are starting from a particular space, you want to maximize how far you can reach. So this is the thought. If you are finding a solution other than this thought, then you are not finding the minimum jumps. Because if you want to go farthest in the minimum number of jumps, you will have to look at the maximum range you can cover. So this thought aligns with the global optimum solution and hence it is valid. One last problem that I want to cover is non-overlapping intervals. And no greedy approach will be complete without this. Probably this is one of the first problems that start to get tricky and you realize, okay, greedy approach is actually something. What you're given over here is, you are given certain amount of course schedules or rather some intervals. So this is a problem written in a lot of different words. Like these are activities, these are syllabus, these are your courses, these are your day schedules. It could be anything. The idea is that you are given this particular time range and each activity has a certain span available. For example, this activity will take 2 hours. This will take 1 hour. This activity is going to take 4 hours. So you have to tell me the maximum number of activities or the maximum number of intervals that you can choose such that none of the intervals are overlapping. Because if you think about it, if you're doing this particular activity, this activity starts in the middle. So you cannot take 2 activities at once. So either you will have to choose this or you will have to choose this. The problem says that I have to find the maximum number of activities that I can finish. Once again, you have to apply the greedy criteria. But what is your greedy criteria? One thought immediately comes to your mind is, okay, I will want to start my activity as soon as possible because I don't want to waste any time of the day, correct? But this approach won't give you the optimal solution because you are right. You don't want to waste any time in the start of the day. You want to start an activity as early as possible. But your objective over here is not to waste time in the beginning. Your objective over here is to complete as many number of activities as possible. So your greed criteria should be different. You should be looking for activities that immediately end. You should be looking for activities that end the soonest. So it gives you more room in the future to take on more activities. Think like this. If I am able to complete any activity pretty soon, let us say I have 24 hours in a day. If I complete the one activity by 2 o'clock, then I have the whole day remaining to cover more activities. However, if I look for the very first activity that is available, it could be possible that this activity is for 6 hours. So I have very less room available. That is your criteria. So what do? I have all of these activities and I have the ending time of all of these activities. This ends at 4, this 6, this 8, this 5, and then 7 again. What you want to do is you want to sort using the end time of each of the activities. When you sort this, your activities or your intervals start to look like this. This activity ends at 4, then 5, then 6, and then 7, and then 8. So this is the idea that I'm going to use. I will take up whatever activity comes to me or whatever activity ends the earliest. Out of all of these activities, this activity ends the earliest. So I will pick this. As soon as you pick this, immediately you will be able to negate some of the activities. Because think about it, this activity overlaps, so you cannot do it. This activity overlaps, so you cannot do it. So eventually what will happen is, these activities will go out of your schedule. I am at 4 p.m. and I complete my activity. What next? You have to choose again. So once again, go for the activity that ends the earliest, because that was my greed criteria and it has to be applied at every iteration. This time, no activity ends at 5, no activity ends at 6, but I have an activity that is ending at 7. So I will keep this activity, and this activity is negated because it is overlapping. So I'm gonna remove it from my schedule. This activity ends here, and now what I have? Once again check, do you have any activity that is ending soon? This particular activity ends at 8. So I will take this activity in my schedule, and this is my final schedule for the day. This is the maximum number of intervals that I will have such that they are not overlapping. No other approach is gonna give you more intervals than this. And try to think, why was the greedy approach optimal over here? Because we are trying to free up our time in the day. So this is just a kind of scenario that you learn when you solve more and more problems. So if I have to summarize everything, this is how I would look at greedy patterns. First of all, identify your optimization goal. You have to maximize something or you have to minimize something. Next, you need to make sure that whatever local optimal solution you're picking up, it should not affect the global optimal solution. This is really essential. And once you have determined it, once you have proved it, then you can start to think about a greedy approach. What you next do is, mostly sorting will help, because once you have sorted things, you get some kind of an indication how to proceed. You know that greedy approaches usually work in a linear time. So you have to start somewhere and then go all the way up to end. And sorting usually categorizes and groups all of the data together. So that comes in really handy. And I would say that this middle step might be optional. It is based upon the greed strategy that you're choosing. This is also very essential. Your greed criteria should ensure that you're reaching the global optimum solution. It should not be that, okay, I will pick this criteria because it seems suitable to me. You have to try and prove its mathematical correctness. You have to try other greed criteria also, because it is not necessary that the first thought that comes to your mind is the efficient one. Once you have done all of it, just keep on iterating and you will be able to prove the correctness. Try counterintuitive ideas. Try to find a thought that is gonna contradict your actual hypothesis. And you will be able to prove by fallacy that the solution that you're discussing or that the solution that you're thinking of is in fact the correct solution. I know that a greedy algorithm doesn't come straight to your mind. It is not something that you can learn. It just comes with more and more practice and with more and more problems that you see. Sometimes a solution that may appear brute force or a solution that comes to your mind in the first glance, that is in fact the most optimal solution. And that is what makes greedy patterns so interesting, and they're always fun to solve. Interviewers love it because the code written for them is pretty small and they will be able to negotiate on it and they will be able to ask a lot of questions to you on it. Because the code is small, it gives you time over telephonic interviews, it gives you time in in-person interviews as well. Because nobody likes to debug or read a code written for graphs and trees, right? So tell me all of your thoughts. What do you feel about the video? What problems did you have? Tell me all of the greedy pattern problems that you have seen, and the comment section will actually become a very good collection of all of the different types of problems. Let me know what other patterns have you seen and how do you approach the problem. I would be happy to discuss all of it with you. As a reminder, if you found this video helpful, please do consider subscribing to my channel and share this video with your friends. This really keeps me motivated and I can make more such videos. Also, a huge shout out to all of the members who support my channel. You guys really keep me going. And as a member, you do get priority reply to your comments and early access to new videos as well. Also remember, you can now schedule a one-to-one session with me and we can discuss about almost anything. Stay tuned for my upcoming video. Until then, see ya.